Yeah.
Okay, hello everyone. Welcome to TMS Talk, Season 2, Episode 1. I'm one of today's hosts. My name is Ruoxing Wang. I'm a PhD student from Purdue University, and my research mainly focused on the self-powered biomedical devices and the biomaterials. Before this event, please let me introduce today's agenda, which includes 4 parts. In the opening part, I will have a brief introduction of our society, as many new friends join us today. Then Professor He will introduce today's speaker, Professor Chen. He will share with us his exciting research progress. It will last 40 to 50 minutes. Please mute yourself during the talk. After the talk, we will have a 30 minutes Q&A session. Next slide, please. Okay. Our society, the Martlet Society, or TMS for short, is a non-profit organization to build a community for young scholars to freely and equally build connections, share our works, and exchange thoughts. In Season 2, we have our traditional events, the TMS Talk for academia, the WBA Talk for non-academia, and the TMS Workshop for skill sets building. In addition, we introduced a special issue at the beginning. The topic of the special issue is based on what our audience and members suggest. So if you have any suggestion for our next season special issue, please let us know. For more information, please visit our website and subscribe our WeChat, Twitter channels by scanning the code. For any questions, please email us. Now I will pass the floor to Professor He.
All right, great. Thanks for the introduction about the society by Ruoxing. Okay, so it's my great honor to introduce our speaker today, Chen. Dr. Chen is my colleague here at UCLA. He's assistant professor in Department of Bioengineering. His research focuses on nanotechnology, bioelectronics for energy, sensing, therapeutic applications in the form of smart textiles, wearables, and body area networks. So Dr. Chen has published 2 books, 140 journal articles, and 90 of them are he serves as the first and corresponding authors that include chemical reviews, nature energy, nature electronics, nature sustainability, nature communication, jewel matter, and many others. So his work was selected as a research highlight by Nature Science 6 times and covered by world mainstream media over 1,000 times in total. And that include the Wall Street, the NPR, ABC, NBC, and CNN. So Dr. Chen, besides these tremendous amount of publication, he also filed 14 U.S. patents and licensed 1 Beyond Research. So Beyond Research, he's also currently associate editor of biosensors and bioelectronics. This year and last year, actually 2020 and 2019, he has been selected as a highly cited researchers in the Web of Science. Dr. Chen is a recipient of many awards, including the highly cited researchers, as I mentioned, and also the ACS Nano Rising Star Lectureship Award, Frontiers in Chemistry Rising Stars, Nanoscale Energy Investigators, and among so many others that I probably couldn't list one by one here. So without further ado, I can't wait to pass the floor to Dr. Chen to start sharing his research progress on smart textile for personalized healthcare. Jun, all yours.
Thank you, Ximin. Thank you for a detailed introduction. Yeah. So I think I will show my slides first. So, okay, thank you. Before my talk, I just want to thank several people. So basically, I really appreciate Bing and as organization and the invitation, and the Jen's organization invitation, and also Ruoxing and Ximin's introduction, and especially Professor Yang Shu was still here. I really appreciate your attendance as well. So today I feel so grateful and humbled to share my research in the past 2 or 3 years. Actually, I just come to UCLA in 2009. So 2019, actually, just a very new assistant professor. So basically, today my talk is entitled "Smart Textile for Personalized Healthcare." So as Ximin and Ruoxing introduced, I'm an assistant professor at UCLA in the Department of Bioengineering. And during my presentation, if you have any question, please feel free to stop me. I hope we can make our talk more like a conversation style, this kind of scientific communication. So why personalized healthcare? Look at this curve. This curve, it describes the disease burden with the relationship with cost. Our current healthcare system is based on typical current intervention. That means, for example, if we have a headache, so the first thing you want to do is to call your doctor, say, oh, I have a headache, and I come to see you. But the doctor say, oh, I will check my schedule. If it's not emergency, probably you have to wait 2 days. 2 days later, you can drive a long distance to a clinic center, and the doctor may give you some treatment. But you can say this type of healthcare system is based on typical current intervention and is very high cost, and is very low efficient. Because, for example, the LA has a very heavy traffic jams, so sometimes it takes a long time to drive to a clinic center and to probably spend 10 or 20 minutes to talk to a doctor, then you have to drive back. And you can say this is very low efficiency, very high cost. So if we could perform early molecular detection, for example, if I have a body temperature sensor on my body, so it's continuous monitor body signal, physiological signal. Or for example, if someday when I get up, if I found there's some abnormalities in my body temperature, maybe this information could be shared with your doctor over distance. So my doctor may remind you, oh, Dr. Chen, maybe you're working so hard recently, so you have a lot of pressure, you have potential to get a cold or get a headache. It's better if you can reduce the working load and take some rest, drink some cold water. Maybe your headache will not happen. You can say this is the proposed personalized healthcare is based on the earliest molecular detection. It can largely reduce the cost and with enhanced health enhancement. And also it's not based on the disease management, it's based on disease prevention. But how to realize this kind of personalized healthcare, I think one of the challenge issues is to develop low cost, affordable, wearable biomedical devices, which could continuously to monitor body physiological information. If we found some abnormalities, it could be share this kind of information with your doctor over distance, then we can take some prevention actions. So then by doing this, we can enable the change of current reaction and disease-centric healthcare system to a personal mode with the focus on disease prevention and health promotion. But how to develop affordable wearable biomedical devices, that's gonna be a challenge. Look at this Apple Watch is one of the very popular, famous, I would like to say fancy biomedical devices which could monitor a heart rate, but it is additional burden to wear. Maybe somebody may don't like the feeling of wear a watch during your typing something or during your working. So, and also it's very expensive. So when I was postdoc at Stanford, I really tried very hard to be cool to purchase an Apple Watch, but it costs 1/5 of my monthly salary. So I eventually give up this idea. So, but I noticed that textile is a piece of indispensable component to in our daily life. Actually, our human beings has a long history with textiles. So if we could develop textiles into wearable biomedical devices, they have certain of advantages. For example, textile has made up from wide range of materials, from natural materials, including silk, wool, cotton, to synthetic material, for example, from polymer, peptide, polyimide, polyester. All of those polymer materials, many of them are biocompatible. biodegradable, even bioabsorbable. So you can see those materials has a lot of advantages if we can make them into textile form and to develop into wearable biomedical devices. But how to develop those materials into wearable biomedical devices, that comes another challenge, because as we know, all of the materials I mentioned here, silk, wool, or polyimide or polyester, those materials are chemical inert. It's very hard to develop them into biomedical devices. So with that concern, so I noticed that actually human body contains a lot of biomechanical energy or biomechanical motions. So if we use different type of working mechanism to develop some device into textile form to convert those biomechanical motion into electric signal, then if we to analyze those electric signal, then we can develop those textiles into wearable biomedical devices. This is just a very rough thinking, but how to realize this? As we know that, so to convert mechanical motion into electric signal, we know that we have electromagnetic effect or electrostatic effect or piezoelectric effect. All of those traditional working mechanisms are able to convert mechanical motion into electric signal. But if we wanted to incorporate those working mechanisms with textile form, definitely they have challenges. For example, the electromagnetic base, we're very familiar with those one. So you need a magnet, a coil. Definitely those materials are very rigid structure, and it's very hard for you to make in the flexible, even soft form. Especially, it's very hard for you to incorporate into textile form. For electrostatic base, they also very complicated structural design, and especially they need a DC voltage to initialize a device whenever you want to trying to use it to convert mechanical motion into electric signal. For piezoelectric bags, so piezoelectric bags, we have used materials which has piezoelectric effect, and a majority of those materials are inorganic material. For example, zinc oxide. My peer advisor, Professor Wang, spent more than 10 years on developing zinc oxide-based piezoelectric nano generator to convert biomechanical motion into electricity. And also they have very few polymer, for example, PVDF. They also have piezoelectric effect. But I would like to say for those type of working mechanism, they have very low sensitivity to the tiny pressure. And especially it's very hard to incorporate those working mechanism to convert biomechanical motion into electricity. And then we can take a further step to develop those textiles into wearable biomedical devices. So then how can we use textile form to convert the biomechanical motion into electricity? So very luckily, in 2012, we invented a fundamental new energy technology. I would like to, is based on the contact electrification. So from very young, we're educated that when you use glass to friction with silk, it generates static charge, and then you can use them to attract small items. Or in the cold winter, when you take off your sweaters in the darkness, you can see the sparkles. Actually, all of those sparkles actually are because of contact electrification. And sometimes in the cold winter, I know in Pennsylvania now it's very cold. So sometimes when you want to use a key to open a car door, sometimes you can get electrified. All of those are just because contact electrification. So actually in a scientific community, there has such kind of table to describe different type of material have different electron affinities. For example, human body, that means human dry skin, is a type of material which has strong ability to lose electrons with a positive charge. Some of fluorine polymer, for example, PTFE, they have strong ability to grab electrons from other materials and get negative charge. Actually, why human skin's contact with this kind of fluorine polymer has electron transfer between the two? One is negative charge and one is positive. Why is this? Actually, is unknown in the community so far. Professor George Whiteside at Harvard, they spent 30 years to understand the physics phenomenon, physics principle behind the contact electrification, but it's still making progress, but is still unknown phenomena. But we don't know what is really happening there, but we use those phenomena to develop a fundamentally new energy harvesting technology. We call it triple electric nanogenerators, TENG for short. How does it work? Let's watch this video. So basically, when two types of polymer, for example, the blue one, the purple one, has different electron affinity with each other. So when we have a mechanical force to bring that two contact with each other, charge transfer the interface, with the result, one will be positive charge, another will be negative charge. As I mentioned, those static charge along mobile can sustain on the surface for a long period of time. If in our ideal case, if we don't consider the humidity, the temperature or pressure in the ambient environment. So if we deposit a pair of thin metal electrode on the back of polymer surface, then when there's a biomechanical force to induce a periodic contact separation between the two charged polymer surface, then they will build up a change in the voltage potential. So this kind of change in the voltage potential will act as a pump to pump electron to do back and forth between the pair of metal electrodes due to the electrostatic induction. So you can see this working mechanism has certain number of advantages. For example, for those contact education is actually the surface charging effect. So they just need a very limited amount of materials here. Usually, typically for the polymer thickness, only 20 micrometers, that's good enough. And for the metal electrode, usually 100 nanometer, that's good enough to make a device. So you can see the total thickness of the device could be controlled under 50 micrometers. And that's usually a diameter of human hair. So you can see the device could be very lightweight, very soft, and very thin. So definitely they have a number of advantages. But as I mentioned, the simple structure allows softer material can contribute here, and especially those softer materials polymers, we can make them into fiber shape and then to be developed into textile by using Weaving lithium technology. And also it's very lightweight and also very low cost, because all of the materials I mentioned here are economic available, and due to the simple structure design, they can further reduce the manufacturing costs. So to make the total cost of the device could be very low. And also we have a lot of materials choice here to fabricate those devices. So based on this working mechanism, I developed a different type of textile product for personal healthcare, especially I want to mention it's for biomonitoring, for therapeutics, and for energy supply. So where energies are part of this big picture of personal healthcare, just because all of the wearable biomedical devices, they certainly need power supply. So that's why energy also is a component of this picture. I will spend more detail to talk about this part. So let's go to the first part, that is the sensing. So the very first application I want to share with you, that is use textile for sleeping quality evaluation. Actually, sleeping disorder is a major health threatening in high-pace modern society, which could result in mood disturbance and also many heart rate diseases. Sometimes, for example, in the morning when your partner get up beside you and get mad with you, maybe it's not because he or she has a bad personality, just because she or she may have a sleeping disorder. So for sleeping disorder evaluation, those are two types of typical current technology. One is use a clinker to click the fingers, and then you have the wild days during your sleeping. And second is use cell phone app. They just use this, put the cell phone on your bed sheet. So during sleeping, your body movement can be detected by the cell phone app. So you can see those technology have certain disadvantages. For example, they have a complicated structure design, and they're made of very high tech. So, and also use a very expensive materials, make them very high cost. And also it's very inconvenient, especially in finger clamps. Maybe that will make your sleeping disorder worse, I think. And also not enough accuracy, for example, this sleeping app, because cell phones have a bulky structure, sometimes is not responsive to the tiny body movement. So with these concerns, we develop a pressure-sensitive large-scale smart batteries is in a textile form, which could to detect your body movement during sleeping. So basically, those smart textiles The smart batteries is large scale fabricated, and you can look at those diagram. We have a number of triple electric sensor rings here to detect the force, and those triple electric sensors are individually addressable. So how does it work? So basically, we just take one single unit for illustration. Look at here, those triple electric sensors has a 3-layer structure. With top is conductive fabric, middle we have wave-shaped PET thin film, polymer thin film, and the bottom we have our conductive fabric as well. So when you apply a force, that will induce a contact separation between the top conductive fabric and the bottom this kind of middle PET polymer materials. Which will induce flow electrons in the external circuit. And we test that these triple electric sensors are very sensitive. Even you use a finger to touch these smart batteries, it can generate voltage up to 3.5 volt. So that means it's very sensitive. And by doing this, we use the sensors to generate a lot of electric signals and to detect body movement in the whole life sleeping. And we construct this graphic user interface. Look at those user interface. We can see that main body doesn't move too much, but the forelegs and forearms moves a lot during the whole life sleep. And I will take a first step to develop those electric signals and analyze those electric signals and develop into a sleep quality report. So we use body movement amplitude to classify the 4 categories, actually 4 states of sleeping. That is a wake sleep, night sleep, or deep sleep. And the measurements continuously from 11 p.m. to 8 a.m. That is actually the time for the tester to go to sleep and get up. Look at the data. Actually, this tester has a deeper sleep around 2:30 a.m. And with a time span 3 hours. That means actually this tester has certain good sleeping behavior. Actually, he or she has 3 hours deep sleep. That means he or she doesn't have sleeping disorder. So we take a further step to develop those textiles into self-powered emergency medical system. So how does it work? So basically those, the first one is a falling down warning system. It's designed for all the people who live alone away from the doctors or sons or family members. So if in a late night, if they accidentally fall down from the smart battery, so we deploy a layer of sensors here, they will generate electric signal. So those electric signal will trigger alarm and also send to the doctor or family member as a message, as a notice, and to ask them to come here to take care of the older men, older people who live alone. And we also take a first step to develop system textile into a self-powered help seeking system. So it's designed for the heavily sick people in the hospital. In the late night, if they need help, they just gently touch the certain area of the smart battery. They also generate electric signal as an alarm and also as a notify signal, notice signal to notify the family member of doctor over distance come to take care of him or her. So that is we just develop those smart textiles not only for sleep monitoring, but also for self-powered emergency medical system for remote healthcare service. So those 3-layer structural textiles actually is non-washable, and very recently, we developed a single-layered, auto-soft, washable smart textile. Basically, look at the device, large-scale fabricated. So we just add some functional unit onto the commercialized smart textiles. Look at this green lines. Actually, those are functional fibers. So look at if we take a enlarged view of the functional fiber, you can see actually it's a co-shell structure. We have metal as a core, and then we have polyester yarns as a shell, and also silicon tube is as an encapsulation layer to make the whole device is washable. So basically, even we put this piece of textile in a tank of water, as long as we can get mechanical excitation, it can still generate electric signal. So by using this singular out-of-soft washable smart textile, we also take a first step to develop those systems for sleep apnea detection. Actually, some of the people may stop breathing during their sleep. So this could be very dangerous if you cannot wake him up or wake her up. This that may lead to death. So with this concern, if we put those smart textile onto the human body, actually well against the belly. So during the normal breath, you can see they will generate a regular electric signal. But as long as he or she stop breathing, they will generate a large fluctuation in the internal circuit. So this large fluctuation could be developed into a warning signal to notify the family member or over distance and then to wake him or her up. Otherwise, could definitely it could possibly lead to death. So this is a smart textile for sleep apnea detection. Actually, smart textile cannot be only used for sleeping-related diagnosis. It can also use for pulse wave monitoring. So here is another design by using non-woven textile. So they also have three layer structure design: top lateral, bottom lateral, and the middle. That is a three-dimensional cellular sensor ring with some piezoelectric nanoparticle inside and also some polymer matrix. So you can see those devices also very thin, only 8 micrometers. Is can well confirm with the curvature of the human skin for the pulse wave monitoring. So we test that before and after exercise. You can see this piece of devices can accurately monitor the heart rate. By the experimental result, we can see the heart rate are changing from 33 per minute to 92 per minute after exercise. So basically, we just calculate number of peaks and divide it by time. Then we can get to know the heart rate. But this piece of textile is lack of wearability because of non-woven structure design. So the breathability is not very good. So if you wear this type of device for long-term monitoring, possible monitoring, definitely it will cause discomfort. So with this concern, recently we really developed a piece of fabric-based textile, which is construct based on the basis of commercialized textiles. It has two-layer structure. At the bottom, we have a silver-coated fabric, and then on the top, we made our flower-shaped devices to make it good-looking. Actually, I think wearable bioelectronics, I think the appearance of the device also very important part of it. If your device very ugly, I think the user may not like to wear this against in the body and walk on the street. So how does it work? So basically, for the flower shape, we have different functional yarns. Each of the yarns, we still use polyester to twist with thin metal yarns. And then when this type of device wear against arteries, the auto vibration will induce contact separation between the polyester and the silver-coated fabric that also generate electric signal. So here, give a detailed view of the working principle of the device. We just take a cross-section of a yarn to say, look at this. If the compression or expansion of blood vessel, that will induce a contact separation between the metal yarns and the polyester yarn. They also generate electric signal. So here is the electric signal generated from the waist arteries. You can see this. We just take a look at the electric signal in one cardiac cycle. Look at those. Basically, 3 typical points, PS, PI, and PD in the pulse wave field can be clearly characterized. So those signals are analog signals. So we take a further step to develop a system for signal processing and transmission. Basically, the general electric signal, analog signal, we go through the filter amplifier and then go to analog digital convention and then use microcontroller unit, and eventually we use Bluetooth and to transmit those digital signal into cell phone app. So in the future, you just wear a piece of textile and check out the cell phone, then you know your pulse wave profile all the time. And here is a video I really wanted to share with you. So look at those. Basically, this piece of textile device. Then here are the units for a singular processor transmission. Here we have wireless receiver, and then the mirrored possible singular could be continuously timely displayed on this desktop. So you can see those are the generated possible singulars can be continuous and timely displayed on a desktop. Why we use desktop? Because they have large screen. Then you can watch those singular very clearly in a video. Actually, it definitely could be displayed on cell phone AVP as well. So that's much about the textile for biomonitoring. The second part, we can also develop textile for therapeutics. So the very first example I want to share with you, that is we use textiles as an assistive physical therapy to perform the wearable sign-to-speech translation. So actually 37.5 million American 18 older report trouble hearing. So, and about 75 of them are unemployed due to the lack of effective communication tools with the outsider. So with this concern, recently we developed our wearable sign-to-speech translation system. It has two components. One has a stretchable sensor unit. Second is a wearable flexible PCB for singular processor transmission. So how does it work? Basically, we take a illustration to show the working principle, one single stretchable sensor unit. So look at those. This fiber is also has co-shell structure design, and also is fully stretchable. So you take a rubber fiber as a substrate, then we use this kind of hybridized this polyester and metal hybridized yarn to twist against the rubber, and then we use TMS as the shell. You can see when we weld these fibers against their fingers, and then when you perform American Sign Language, it will induce contact area change between the TMS and the polyester. Those two types of material have different electron affinity, and eventually will generate electrical signal in the internal circuit. So we weld those systems on our 5 fingers, and so somebody raise their hand. So is there any question from the audience? Okay, so basically when we weld those systems on the hand, when you perform standard American Sign Language to express, for example, the letters ABC, the numbers 1, 2, 3, or the short phrase, those I love you, here you can see those generate electric patterns from the 5 fingers. So by analyzing those general electrical patterns, we can perform the sign language to speech translation. So basically this lab scale demonstration when weld these devices, and then the sign language will translate to voice, and by using cell phone app, here are user interface in the cell phone. Basically when you perform the sign language, and then this sign language translate into voice, and then here are the electrical patterns for each of the sign language component. So here is a video I really would like to share with you to visualize the operation procedure. So
I L Y I love you.
So basically, you just weld this kind of lightweight system, and in the future, you just perform American Sign Language, and then could be translated into voice. So this work recently received more than 200 media coverage in the world, including the NPR, the Discovery, the ABC, NBC, CNN, and BBC, all of this. And especially is highlighted by Science. And also recently is get the top 10 science story of 2020 by OSC from Canada, is a scientific community in Canada. So that's much about the textile actually is a yarn for therapeutics. So the very third part, that's energy. So why energy is this part of personal health care? look at those future wearable biomedical devices. Here's a wearable circuit for biosensing. And here is a wearable ultrasonic sensor for the heart rate monitoring. You can see how those wearable biomedical devices, certainly the power source drives them. But I would like to say this beyond the capability of batteries, because batteries have a very rigid structure design and they are made of toxic element, and it's very hard for you to incorporate those components into those thin and lightweight wearable biomedical devices as a power source. So how to drive those future wearable biomedical devices that could be another concern. So look at clothes. Actually, everybody wear clothes and go to work. And we also have a lot of renewable energy sources available. So for example, the solar radiation and the mechanical deformation. So if we can use textiles to convert those renewable energy into electricity, then it definitely could provide a sustainable power source for the wearable biomedical devices for personal health care. So here is the very first design. I use textile to harvest energy simultaneously from solar radiation and the mechanical deformation. So for the mechanical energy harvesting, we also use triboelectric textiles, which could convert body movement into electricity. For solar cell part, we use a dye-sensitized fiber-based solar textile to harvest the solar energy. So experimental results demonstrate that with a size of 5 centimeter by 4 centimeter, this piece of fabric under one time condition is can stably deliver power output more than 0.5 milliwatt from a wide range of loading resistance from 1,000 ohm to 1 mega ohm. And we show that those pieces of textile was capable to charge a cell phone directly, and also with these small pieces on the wear against the west, it can use to sustainably drive an electronic watch. And certainly it could be used to power the future wearable biomedical devices as well. So actually, textiles cannot only to use to harvest energy from biomechanical motion and solar radiation. Actually, textile can also harvest energy from body heat and biochemicals. So recently, by invitation, we published a review paper on chemical review. Is entitled "Smart Textile for Personal Health, Smart Textile for Electricity Generation," and is systematically summarize all of the progress by using textile as a sustainable power source to generate electricity. If you have interest, you can read those papers. And energy harvesting devices, they have shortcomings because they usually have output fluctuation because the energy input from nature environment is not stable. So with this concern, we recently developed another piece of fabric, which is hybridization with the fabric solar cell with fiber batteries. So that means the fabric solar cell could convert solar radiation into electricity and simultaneously charge the fiber batteries. So here is the data showing. So during the photo charge, the batteries could be charged. So at this discharge plateau of fiber batteries, then they have stable electric output. No matter you twist the fiber or you walk into the shadow or there's a raining day. So you can see definitely by using the regulating capability of fabric batteries. So this piece of textile could provide a sustainable and a stable power source for wearable biomedical devices. So that's much of our talk today. Basically, I just pick up several examples to show how can we use smart textiles for biomonitoring, for therapeutics, and for energy. And I really would like to acknowledge the Wearable Bioelectronics group at UCLA with a number of postdoc and PhD students, and also the collaborator contributors, and also the funding agencies for the financial support. And thank you very much for your attention. And please feel free to ask me any question if you have, and welcome you to the city of Los Angeles. Yeah.
All right, very fabulous talk with so many different type of applications based on this amazing TNG mechanism developed only like 8 years ago, right? Yeah, so let's see if we have questions from the audience. Okay, yeah, so please feel free to either type your questions in the chat, or you can probably, I guess you can unmute yourself to ask directly, right? Yeah, so,
Yeah.
okay, we have someone raised hand, Sheng Jiegao, right?
Can you hear me?
Yes.
Sure, yeah, we can help you, yeah.
Okay. Okay. Hello, Professor Jun. This is Sheng Jiegao from Purdue University. Thank you for your presentation about the biome application in TNG area, which is very impressive. So here I have actually two questions. The first one is about the sleeping monitor you mentioned. So I know there's some research group and company using the piezoelectric based PVDF to make a stripper and hide under the bedding to monitor the human activities based on the D31 effect from PVDF. So in my personal opinion, I think the tactile-based TNG sensor can provide a much more convenient fabrication and system integration platform compared with using the piezoelectric sensor. But other than that, from the signal perspective, so what is the advantage of using the TNG?
So basically, I would like to say TNG is much more sensitive and piezoelectric based devices, because for the triple electric based devices, they usually very easy to get electric output up to 1000 volt. So this make if you take those voltage signal as a sensing element, definitely they will have very high signal to noise ratio. Compared with piezoelectric based, definitely the output usually at several microvolt or hell is millivolt. So definitely the signal to noise ratios is not comparable with triple electric based devices.
Okay.
Yeah.
So generally speaking, it will make it much easier for the following signal processing, because
yes,
the signal
that is true. Yeah,
is much higher than the piezoelectric based one.
Yeah,
okay.
That's true. Yeah.
Okay, my second question is also related to signal. So in your page 13, so I think the demo you showed after this slide is actually quite impressive with a very stable baseline. From what I know, for those the expensive ECG sensor like the one in the Apple Watch or the Fitbit, they will somehow use a gyroscope to overcome the signal drifting problem during the measurement. But your sensor, the demo you showed, the signal is very stable with very obvious peak. So my question is, how to avoid the signal wandering problems, like how to avoid the signal drifting problems because you attach the sensor on the rest. And is there any extra consideration, design consideration during the sensor structure design to overcome this drift problem?
Yeah, this is a very good question. So actually, this is one of the largest challenge currently in the field. So for all of the demonstration I show here, I assume you just stand still and don't move your body. And for this kind of singular drift problem, we can take effort in a perspective of software. We can use algorithm to reduce the drift. But as you said, there's some noise induced by a body movement. So actually, this is a very hot topic in the field. So very recently, we just finished a project. We just want to develop another sensor which could stably have stable electrical output. Stably convert a biomechanical motion into a true signal, even you have a body movement, this kind of concern. So to solve this problem, first we can to design more fine the structure of the devices, and second we can use a machine learning algorithm to get rid of those noisy signal, because those noisy signal usually have different pattern with possible electric signal, and also they have different frequencies. So probably we can tackle this problem from both hardware and software. And this problem is still waiting for a perfect answer. So we still spending effort in this direction. Yeah.
Okay, thank you very much.
Thank you, Shenjie. Thank you for your question. Yeah.
Okay. After this first couple of questions, we have another question in the Q&A box here. That's from Alham woody, right? So the question, thank you for the great talk. Would you think, what do you think should be the future direction in this field? Chen, please.
Okay, the future direction of the field. So the future direction, I think definitely all of the research result I show here is more like a proof of concept. So the future direction of the research, probably we have to solve a lot of problem here because this is really an emerging field. Smart textile for personal health care, both smart textile and personal health care. These two terminology are very new, a very emerging terminology in both the scientific community and also the industry. So if we wanted to develop those projects, I mean, I should demonstrate here to a commercialized product. I think I would like to say first the stability of the device could need to be enhanced because for smart textiles, definitely we need to contact with perspiration or environmental humidities. And here a lot of devices I show here is not waterproof or humidity resistance. So we definitely need to spend effort to either design the device, use more advanced materials or use more fine structure design to enhance humidity resistance of the devices. And certainly we have to, as in the meanwhile, have maintain the wearing comfort. And thirdly, I think as Shinji just mentioned, for all of the demonstration here, we just assume the body stays still, but for the real wearable applications, people may move a lot. So we certainly need to use the machine learning algorithm or some other method to solve those problems. Even we can mirror the physiological information even during exercise, even during sports. So definitely they have a lot of challenge up there because this question is very generous. So due to time limit, probably I just simply point out 3 points. Yeah, I certainly there have a lot of other problem in the field waiting for an answer. Yeah.
Okay, very good. So Jun gave the answer from the perspective of this whole field in the development and also some technical challenges like the stability, right? So thanks for the answer. We'll be welcoming more questions.
Yeah, so Jun, very nice talk. I was wondering, so when making these textile, are you doing this hand sewing or knitting? Are you actually integrate those things into the commercial machine? Because I think eventually, if you want to commercialize this, right, you cannot use your hand sewing.
Yeah.
Because all these yarns are very delicate. So
Yeah,
what do you think
true,
the challenge in that area?
Yeah, that's a very good question, Professor Yang. Yeah, thank you for the question. Yeah, certainly for the majority of textile demonstrate here is use hand weaving. So if we wanted to use a weaving machine and a knitting machine to construct the fabric, certainly the mechanic strength of they have very strict requirement for mechanic strength. So for some of the function there, we have to use, for example, for the solar textile part, we use, especially the source, we use functional coating. Actually, those coatings very fragile, sometimes very easy to get peel off from the polymer fiber substrate. Certainly for this piece of device, we have to use hand weaving very carefully and to make a device. And this is, I think this is a very large challenge in the field. But for some of the other devices, for example, for this piece of devices, certainly because we use a silicon tube to protect the whole device. So I think those devices could be has sufficient mechanical strength to go through a weaving and knitting machine. And so to answer this question, so I think definitely this is very challenging, but we have to still spend the effort to enhance the mechanical strength and meanwhile to maintain the functionality of the fibers. And I hope in the future, eventually we can use a majority of the, to construct a majority of smart textile by using weaving and knitting machine. But in the current progress in the community, we have to admit that, or we have to consider that most of the textile by use hand weaving very carefully, especially for those use functional coating devices, functional coating to construct those kind of fibers. For those kind of type of device, we certainly need to use hand weaving, very carefully, So I consider that a lot of demonstration here is more like our proof of concept,
Yeah, I think the other challenge is because there's a human varies from human, right? So when you wear this, and obviously, especially close to the body, there's a lot of sweat coming out or the perspiration from the body. So how do you make sure they actually continuously monitoring this? When is continuous monitoring this without considering all these moisture coming out, affecting your signal? The other thing I was wondering, because in the first application you demonstrate is if the people fall, you can basically pressure sensing. So I think the challenge is how sensitive is sensitive, because if it's too sensitive, you get a false signal. If it's not sensitive, and you don't get the right signals. I think that there's a lot of questions. How do you balance this, and how do you you're trying to mapping them out, right? I think the mapping out is probably the right direction.
Yeah, I think that to solve this problem, we can either to enhance the design of device or use more advanced materials to construct structure from the hardware perspective. And also nowadays, the machine learning algorithm is very popular. So, or deep learning. So probably we can use those kind of software to get rid of noisy signals from the falling or from other noises that is not related to physiological information. And also I would like to say, so for the perspiration, certainly this is a big problem for all of the textile you wear against human body. Certainly we have perspiration over there. So I think for those functional smart textile, either we can use just like very unique use, for example, space exploration. So those textile is not need to directly contact with human skins. And also we can use encapsulation layer to prevent them from the humidity or perspiration. This is one of the solution to solve this problem. And actually, I think this problem very hardly. And recently in our group, I'm developing another fundamentally new working mechanism, which could fully waterproof, and it's not based on either piezoelectric or triboelectric, but it's still on the way. So I would like to see we can also design a different type of other devices with different working mechanism to solve this problem. So this is a very common challenge for all of the wearable bioelectronics in the perspiration and this kind of wearing discomfort, and this problem definitely we need to solve step by step in the community.
All right, thank you.
Thank you, Prof. Yang. Thank you for the question.
Right.
Wonderful. So it seems, Chen, you're implying some new mechanism that make us so curious. So we're so looking forward to your new work in the near future. Right? Okay.
Thank you.
Actually, since you have the slide here, just a short question. So here, this one, which has a relatively simpler design of this each fiber, each yarn, right? So this is not hand woven, right?
No, for this one?
Mm-hmm. This is 10 meter. I mean, this is entire.
This one we can use a machine to weaving or knitting it, because actually just a functional fiber which has which is encapsulated by a silicon tube. So that means they have certain very high. They are stretchable and are also with very high mechanical strengths, and then we can use them to weaving or knitting.
Okay. I do have more questions, but I will save a little bit for later.
Can I ask a question?
Sure, Bibi.
Hi, Professor Chen. Very impressive talk and a lot of work during your past PhD and the postdoc and even assistant professor. Very impressive. Actually, today I have two technical questions. The first question is about the following up question to Professor Su Yang's question, Because as I know, TNG is the signal of TNG is very sensitive to humidity.
Yeah, that's true.
Right.
Yeah, this is based on the surface charging effect. Yeah.
Yeah. So, but if like during if considering your TNG for sports monitoring and there's a lot of sweat, do you have any like current thoughts to solve this issue for this kind of application?
You mean for triple nano generator, right?
Yeah. For this kind of sensing.
Yes, so definitely to solve this problem, we have to use the encapsulation layer to protect the functional layer away from the perspiration and the water. Yeah, definitely the humidity definitely make the device don't work. Yeah.
Okay.
Yeah, so we have to use the encapsulation layer to solve this problem in the community so far. Or you want to construct some super hydrophobic surface, and this could also enhance the water resistance a little bit. Yeah. For example, if you want make the two triple layers, for example, make the video here, which for the purple one, the blue one. So probably if we for the triple layers, if we use some functional super hydrophobic coatings. So some of experimental research shows that if we make the device, the surface super hydrophobic, so it could enhance the water resistance or humidity resistance of the triple nano generator. Yeah.
So I'm not sure whether this kind of coating can still like keep the sensitivity performance of the device. Do you have any like insight?
So probably, yeah. So the super hydrophobic surface could definitely help the surface get rid of the water. Yeah. But if there's some water goes into the surface, definitely we need to get rid of it before we make it work. Yeah.
Okay.
Yeah.
Thank you.
Yeah, I think I follow up with Bing is once you put a coating, you put an insulator there, right? So your whole point for the triboelectric to work is you want this two opposite charge material to be close to each other. But once you put a coating, you're separating them. So although you can control the water, you're preventing the water, but you may actually adding the insulating materials in between. So your interaction between these two sets of opposite charge material will be actually diminished.
Yeah. So to construct a super hydrophobic surface, we have two ways. One is from a chemical way, as Professor Yang mentioned, we can use a functional coating to add additional chemical layers and to enhance the super hydrophobic. And simultaneously, we can use nanostructures to physically create nanowells, nanopools, nanoroughless on the surface to make it construct a super hydrophobic surface as well. Some of the research shows that for the PTFE is intrinsically hydrophobic. So if we create some nanowells on the to enhance the roughness at layer scale of the PTFE surface is good to reach. The contact angle could reach 160 degrees C to make them super hydrophobic. Yeah. So by doing this, actually, this roughness first can enhance the super hydrophobic to enhance super hydrophobic the capabilities, the super hydrophobic capability of surface. Second, this roughness could be lead to a higher generation static charge because this kind of roughness could enhance the effective contact area. Yeah, actually, this is one stone, two birds procedure. Yeah.
Okay. I have another question about the slides 9.
Yeah. Sure.
It's a little bit not. I'm not sure because I found the material in slides 9 you use like silver, right?
Yeah.
Yeah. For silver AG in the bottom left figure, there's a gray one. Do you use silver?
Which one? You mean in these slides, right?
Yeah, in these slides.
Yeah. Yeah, we use conductive fibers here. But for this one, we use silver. Yeah. You mean this one? Yeah. Yeah.
Oh yeah. So for the silver, I'm not sure the like long-term stability when you touch with get in touch with the human body or something else, because like they may react with the sulfur. The silver will react with the sulfur to form a Ag2S layer. Maybe you will. It's kind of. Just my curiosity about this question.
Sure. Yeah, this is a very good question. Yeah. Certainly the silver could be oxidized in the ambient areas.
Yeah.
So definitely long-term operation of this device, the stability of the device is a concern. Yeah. So to solve this problem, as I said, we probably need to add an encapsulation layer of the to protect the device. So for all the demonstration here is more like a proof of concept. So we don't consider the long-term stability of a device at a current stage. Yeah.
Okay.
But we can, for example, we can put the device in a very dry places and to get less oxidation to for example, you can put the device in a good place. Probably this is another simple way to enhance the stability of a device, just like you treat some precious or medical devices to treat them. Don't put them just in the ambient environment. This could be a problem to solve this. But certainly your question is a concern. For the demonstration here, we just use as fabricated devices. It's not we don't consider too much about stability. So this is more like a proof of concept. We still need the effort to polish the system to make it more stable and more could be stable in the ambient environment. Yeah.
Because the reason I ask this question is recently I'm doing a short-term industry intern in a textile computing company, and these guys always use silver, and they do have this kind of industry questions. So they are thinking about how to handle these issues in the development stage.
Yes.
Okay. So yeah, that's my technical question, and I think I can give the floor to other audience. If there are more times, I can ask more like general questions in the end of the talk.
Okay.
Professor Chen, I also have one question just for these slides. So for the right work, the flower-like shape, I really appreciated the design. I think people usually like the beautiful devices, but I really appreciate the beautiful design. But also I have a question, can we make it be the functional patterns? So we can design the patterns to improve the sensitivity, or we can print the certain type structure to improve the stretchability of the device. So is there any possible design for TNG device to improve their functionality, not just the appearance?
So I beg your pardon. So your question is to make a device stretchable?
I mean, like something like that. So improve the functionality of the devices from the pattern design. So I just use the serpent type structure as an example. The serpent type structure can make the device more stretchable. But in TNG, is there any other patterns that possible to help our device?
Oh, so you mean can we add some design to enhance stretchability of the device? Your question is this, right?
Maybe not only the stretchability, also sensitivity, any possible functional performances.
Yes. So so for this design, why we use a flower shape? Just because we want to make the device good looking. Yes. So this is a reason we want to design the devices in this shape. Yeah. Because just like in a flower shape. So actually, the real workable unit of device actually just those yarns. Look at those yarns. We just take an illustration of one yarn. So and also look at those working principle. Basically, we have cross-section view of the yarns. Basically, the yarns is the only functional unit. So if you don't put those yarns into a flower shape, or even you just align in parallel in the silver fabric, it can still works, I think. Yeah. So I think the flower shape just like to make the device more good looking, yeah, better looking, yeah.
Okay, thank you. It really looks good.
Yeah, because I think for all of wearable biomedical devices, the appearance of device is very important because the device, if even it's functional very well, in the future people may think it's very ugly, so they will feel reluctant to wear them and walk on the street. Yeah.
I think that's another advantage for tactile, because tactiles you can make it to be beautiful design, but for films, it may be a little bit hard to make it like patterns like that.
Yeah, that's true. Yeah, fiber is very hard to be played with because they have round shape and especially for the tiny fiber. So yeah, and you have to maintain the mechanical strength and also to add some function layer on to add some patterns. Actually, they have a lot of challenge over there. Yeah, compared with the synthetic-based devices. Yeah.
Thank you for your answers.
Thank you, Ruoxing. Thank you for your question. Yeah.
Hello. Okay.
Oh, sorry, go ahead. Sorry.
Thank you so much. Hi, Dr. Chen. Thank you so much for very interesting talk. I had just a kind of general question. Do you think, apart from textiles, do you think that if the triboelectric concepts can be applicable for to fabricate like implantable sensing devices, like out of biodegradable materials or so on? Yeah.
Yeah, Elham, thank you for your question. Yeah, so here for all of the content I present here is for wearable. Actually, triboelectric could be made for implantable as well. So if you just use some biocompatible materials, or even biodegradable materials, and then to make a device whole implantable. And some of the previous research that demonstrate that they could use the device to implant in the human body and convert the heart beating into electricity to extend the lifetime of the pacemaker. So they have such kind of demonstration. Yeah, the device could be implantable. Yeah.
Thank you very much.
Thank you for the question. Yeah.
Hello, Professor Chen. Can you hear me? Yeah, this is Chen Kwang from a postdoc in Leibniz Institute. So I have a question regarding this slide. How do you fix the like the sensing patch on the forearm? So you use some regular PSA tape or some other adhesive materials?
Oh yeah, basically for here, so for the lab demonstration, we just use a tape to fix the device onto the human skin. Yeah.
Okay, so but for the tape, is that like reusable if you tear it out? Like if you put it again, or that still can be adhered on the skin, or
I think for this is just could be just for the medical tape. I think could be reusable. Yeah.
Okay, thank you very much. So my second question is regarding the very amazing line language translation to the Apple app. Yeah, the speaker. Yeah. So that's very wonderful, like one-way communication for deaf people can like communicate with the other like normal people. But do you think about like the other way communication? If I can like speak to a like device, and the device can like guide the glove to make me, if I don't know how to use the sign language, but I just wear this glove, and then it can help me to like do this sign language to communicate with other deaf people. So this.
So you mean when I talk to the glove and then to make a finger move?
Yes.
Okay, I think this is a very good idea. Just like eye-opening, but I would like to say it's very hard to be realized. Yeah, okay. Because to move your finger movement, to make your finger movement, they have very large mechanical force, right?
Yes.
So that if you and also this is I think this idea is very good. It's very eye-opening. So, but I think if we can realize it, definitely you can publish a Nature Science paper. Yeah, but I think it's very hard. Yeah.
Okay, that's just an open question.
Okay.
All right.
Yeah.
Thank you very much.
Thank you for your question. It's a good question, but I think because I think the voice, you first have to recognize the voice and convert the words into certain electric signal. So those electric signal then are the trigger signal or command signal, command to induce some, to control some component to induce large mechanical force to bend the fingers or something. And also bending has to be, yeah, I think I also for a human being, if he or she is alive, so when you move his fingers, sometimes the nerve will have some response to make a resistance. So I think this definitely there's a lot of challenge problem over there. But this idea certainly is very eye-opening. Yeah.
Okay. All right. Thank you very much.
Yeah.
Okay, let's see if there's any other question from the audience. I know our several hosts are waiting for answering question, right? So maybe now is good time, Chen, if you want to ask. Unmute yourself, please.
Yeah. Hi, yeah, Professor Chen. I think it's really a great talk, and a lot of things, a lot of research you do, I think it's really can be useful in some real applications. And I just have one question on the there's an application you made on to detect if the old man has like falling down on the floor. I don't remember which slide it is. And yeah. So I'm just like curious, like how the how can you like did you design some like some, for example, like some code or some app like can for example detect the acceleration of the people falling down on the floor? Because I'm just like wondering if just the old man might be just want to work out and lying down on the floor, just work out, or you know, or just want to chill out on the floor. So can the system detect the acceleration? Because falling down and just lie down, the acceleration probably will be different.
Oh, okay. So for this smart bedsheet, we just deploy a real center, an Agile smart bedsheet. So
yeah.
So that means as long as you touch this, they will trigger an electric signal. Yeah.
Yeah.
So probably your problem is that we have to differentiate in different cases. For example, if you accidentally use acceleration to differentiate those two procedures, this is your purpose of the question, right?
Yeah. So I'm just wondering if there's you have this kind of function in your system. Yeah.
So for this device, certainly we don't have such kind of function. It's just like a 0 and a 1. So you just touch it here and then generate electric signal. But we only deploy the sensor at the very edge of the smart bed sheet, and also here just a certain area. Yeah, for the other areas, there's no kind of response to the mechanical force, but only this help-seeking button and also this kind of a ring of sensor at the edge of smart bed sheet. So this part just like a functional unit. Yeah.
Okay, I see.
For other part, there's no response to the mechanical force input yet.
Okay, I see. Yeah, thank you.
Thank you for the question, Jenny.
Yeah.
Thank you.
Yeah, thanks.
All right. Any other questions? Maybe I can fill in one question. Jun, so we saw several different applications, and we also saw several different designs from the very basic like sandwich design, and then to this developed this fiber-based woven textile. Yeah. So for different applications, or at least within the sensing or therapeutics application that you show here, could you elaborate the design principle here? Like for example, for the several active component to form one fiber, right? So how do you select the material and how do you design their shape to put them together in the most efficient, high performance way?
Yeah, so it's a very good question. Let's go back to the working principle of the device. So basically, to make we are using triple electric nanogenerator to convert the biomechanical force into electricity. So in order to enhance electric output, so probably because those device's output, it highly depends on the effective contact area. So usually we have to create nanostructures onto the triple layers to enhance the effective output, to enhance the effective contact area, and eventually to enhance the electric output. And then that is the singular to enhance the singular to noise ratio. So this is one of the problem. Second, for materials choice, we have to choose the materials which has the largest electron affinity differences. For example, if we use human dry skin to contact with fluorine polymer, definitely they will generate the highest amount of static charge. If you use glass to contact with silicon, definitely they will generate a smaller amount of static charge. So that means when we choose materials, we have to use the materials which has the largest electron difference between each other to assure a higher electric output. Second, so when you choose materials, certainly you have to consider if this application scenario requires the biocompatibility of the device, certainly you have to choose biocompatible materials. So definitely there are a lot of factors or parameters we need to consider for different application scenarios. So for example, if we wanted to get some stretchability of the device, for example, here, just like for this sign language translation, so we have a fine design device to use not use commonly use a fiber, polymer fiber. Instead, we use a rubber fiber to enhance the stretchability of the device. So that means we have to look at the different type of application scenario to choose the materials and also to design the devices. Yeah, I hope I answered your question.
Yeah. That's really good from the like a geometry factor and the materials, physical, the electrostatic, the charge perspective. Yes. And also the mechanical property. Yes. So what I was going to ask. Oh, yeah. So in your slide 6, you show pretty short list of choices of materials, right? That already give you a lot of choices for you to mix and match, right? So I wonder if there's any like kind of confinement or kind of criteria for the materials of physical property need to meet in order to be in this list, for example.
Actually, I'm sorry, I don't quite understand.
Or like in another word, like can you just randomly pick any materials, right? So
so basically, almost all of the material around us has itself electron affinity. So if we choose a two-term, as long as they have difference, they can generate static charge. But sometimes maybe the difference very small. I mean, the electron affinity difference very small. Probably the electrical output very weak, so it's sometimes not detect, and sometimes it's not detectable. And also this kind of static charge, we have very dry environment, and also the pressure and the temperature, all of those ambient parameters could contribute to this part. I mean, some negative impact or some positive impact. Yeah.
Okay, so it sounds it's really truly broad. For the choices.
I think almost all of material, including just people just now they ask a last question about the water resistance, perspiration. Actually, water is also a type of triple materials. Some people show that they use water to friction with other type of material. They can also generate static charge to cause energy from the raindrop.
That's very attractive. And also in the list, so for example, this leads to my next and last question. So here we have metal, right? And we also wanted to look at the mechanical stretchability for some variable electronics, right? So I wonder if you see any kind of constriction or limitation of using metal in your project so far, for example. So probably you would prefer to have some alternative material to replace metal here.
Yeah, this is a very good question. So metal, so far, metal is just like our electron translation layer. So definitely, I think any of the metal can be used here, but usually for wearable application, we consider a lot about the cost. So we just use copper, aluminum, those kind of non-mobile, this kind of metals, we just because very cheap. For example, if we want to construct a implantable 3x2 nanometer, certainly we have to use platinum or gold or magnesium. Those kind of metals biocompatible and to a functional unit. And also certainly metal is rigid, is lack of variability. So we are also considering some conductive polymer to replace the snail to make a whole device more flexible, more stretchable. Yeah.
Then did you see any limitation of the current conducting polymer when you replace them? Replace a metal using conducting polymers?
If I use conductive polymer, certainly the performance could be compromised. Yeah, because this conductivity is not comparable to metal. So, but certainly in another way, we can enhance the flexibility or variability of the devices, or even the water resistance. Yeah, this kind of. So definitely we have to make. There is a trade-off here. Yeah, and also conductive polymer is very expensive. Yeah, so this is another concern. Yeah.
Yeah. Okay, great to know. Okay, I would definitely make an appointment with you to have a follow-up discussion after this.
Sure,
yeah.
Sure, yeah. Sure,
okay,
yeah.
all right. I want to leave time for other members here. If any other questions?
Hao Shi. This question from Hao Shi.
Hello, Professor Chen, and thank you for your impressive PPT and for us. And I have a small question, I see your PPT about maybe the page 6 and the nature electronics there.
Okay,
and
page 6.
Yes, nature electronics. No,
this one.
50 maybe.
Okay, this one.
It's not. And I can show my small question. And do you consider the sensitivity of the electrical signals acquired from the human body? And I think if you can fabricate your devices and you show, and I think the sensitivity of the fabricated devices is very important. So what about the magnitude of the fabricated devices in your work? I think.
Oh, so
sensitivity, yeah.
Yeah, sensitivity certainly is very important for the biomonitoring. This kind of application. So for this sensing product, sensitivity is very important. So your question is that magnitude. So
magnitude, yes, magnitude of the sensitivity in your devices. Yeah.
Magnitude of sensitivity. So you mean the magnitude of sensitivity?
Yes. Yes. Now you can fabricate your devices, and you can get electrical signals from your devices, and you acquired your electrical signals from your devices. I want to know the signals sensitivity. How about the sensitivity of your devices? Sensitivity and the sensitivity to your to the human body, and this is the feedback from human body. I think this point is important for electronics devices. I think, yeah.
So you want to know that exactly the sensitivity value of the device, right?
Yeah.
Okay, so I didn't put the data here. So I think for different application scenario or for different device design, they have different sensitivity. So for example, for this device, the sensitivity usually in our community, especially the 3x2 nanometer, we use the sensitivity is described as voltage per Newton. So that means how large is when you apply 1 Newton force to the device, then how large the voltage could be generated. I know for the traditional sensor field, they use Gauge factor or some other parameter, but for our community, we use just voltage per Newton. Use this unit to describe sensitivity. But typically, I think the the sensitivity of device could be in a range from several, could be up to 100 volt for 1 Newton. Yeah, that's possible. Yeah. Yeah.
Oh,
Voltage
okay.
per Newton. Yeah, and also some devices they have lower, for example, 2 volt for Newton. That's depends on different type of device design. So they have, for the reported data, they have wide range from several volts per Newton to even 100 volt per Newton. Yeah.
Okay, thank you, thank you. I think this part maybe for further research you need to improve this part, I think.
Yeah, because yeah, for in this triple electric nanogeneration committee, so all of people just define the sensitivity by use how much, how large is how much voltage or how much current per Newton to describe the sensitivity. Yeah.
Yes, yes. Thank you for your answer. Yeah.
Yeah. Thank you for the question, Hao-Xu. Yeah.
Hi, Professor He. Professor He.
Yeah.
Because we almost run out of time, but I'd like to ask one more question in the name of TMS.
Sure.
Okay.
Yeah, because TMS is a platform for scholars, especially young scholars, to communicate, especially in the pandemic, right? So, and as I found, there are 4 professors in today's panelist, and I'd like to engage each of you. Could you share your experience for like building a research group, research team, like which kind of criteria of for recruiting PhD and master student, and also how to select research areas? That's my question. So any experience that you want to share with the young scholar, the audience here today? So maybe we can just begin with Professor Chen.
Oh, okay. Actually, Professor Yang is more prestigious and a more established scholar in
we should let the young folks to talk. Yeah, I think both Jing and Ximin, you're very successful building your team, so you should talk.
Oh, Ximin, okay, you first. You are.
No, I was going to say, what is very truly impressive is for such a short period of time as assistant professor here, you can see Chen has published so many high-profile, really impactful papers. I'm always, curious about how he selected a very productive, very good students to build the, the new team with him. So I think we are all waiting for you to share with us, please.
Okay.
I will definitely follow. Yeah.
So, okay. I really wanted to feel humble to share some of my experiences. Actually, I spend a lot of time in hiring students, because I think if you have a PhD student, he will stay with you for 4 or 5 years. So you'd better to spend more time before you make a decision. So I'm very actually very careful about this product. For all of the, actually, so far for all of my PhD students, they either come to my lab to do a summer intern for 3 months, we stay together, or I think, and also some of the students also first they came to my group as a visiting student. They may spend more than 1 year to stay together with me. So then by this kind of collaboration, then and working together, then I will make decisions. For all of the students, I didn't know each other. Definitely, I will not hire them. So, so I think that's as my peer advisor and postdoc advisor, they all said, I think the labor is the most valuable part for lab rather than the equipment or some things. So that's mean actually I really spend a lot of time in finding good students. Yeah, and for example, for one of my student, I just share you what the story, but time allowed. So that student is from Zhejiang University. Is when he sent me email, wanted to show his desire of join my lab. That's in 2019 July. That's just I started my group at UCLA, and at that time he was a 3rd year undergraduate at Zhejiang University, and And actually, he sent me email previously. When I read the email, he just so because the GPA is not very high, and also there's no publication. So for our students who contact me, I only interview those students who has first also publication in our journal which has a impact factor more than 10. I only interview those type of students. So for that student, his name is Gori. So for Gori, I just didn't even, I just encouraged him to apply. But turned out to be after I replied his email 2 weeks later, he just fly to Los Angeles, and he gave me a phone call. Doctor, I really wanted to come to see you because I was already in Los Angeles. And then when they come, then I just relook his CV. The CV really just so. But he said he was a summer intern UC Davis, and he will go back to China in the following 1 week. And I said, because you're about to go back to China, so why you want to see me? He said, Dr. Chen, if you really want to give that chance, I can extend my stay for another 3 months and working together to show you my capability. So I really feel a deep touch of this kind of persistence of the student. And then he just gave a phone call to Zhejiang University and delay his enrollment from September to December. And then he spent 3 months together with me, working together with me at UCLA. And he's really hardworking. And he never published a paper, but he trying to working together with me for the review paper. I show you just now this chemical review. Actually, it has 800 references in this paper. And I say, okay, well, I said you can try this review paper. And then he spent 3 months to finish this. And he was this is his first also paper, yeah, and first paper, yeah, and actually the first also paper. So actually in the 3 months, he demonstrate his capability. Even he has very low GPA from Zhejiang University, and but that is the I have compared with other students. This one is the one I want to hire most, yeah. So I don't care much about the GPA or I just want to see the personality of a student. If he or she really wanted to do research and demonstrate his persistent and also demonstrate his really hardworking. And yeah, I really I like this kind of stuff. I think for all of for the intelligence, I think all of the people around us, most of them are not too smart or not too retarded, and most people just a normal distribution. Some, for example, Einstein definitely that's very super smart. So I think for materials research based, I think the hardworking and the persistence, the most valuable features I really want to look at. Yeah. So you have. When I was at Professor Junior Wang's lab, some students very smart. They are the champion of the Hubei province in a college entry examination, but he or she never going to do experiment, even very smart, but they have very low delivery during the PhD study. So I think the hardworking persistence is very important for the student. I really wanted to look at rather than the GPA or some other parameters. Yeah.
Thanks so much for sharing your story. So basically, for our young students here, you hear the keywords hardworking, perseverance, and you show your enthusiastic, the commitment to interest in this field, right? Yeah. So that's very helpful experience for our other junior faculty here to learn. Professor Shuyang, do you have a few words to say before we wrap up here?
Yeah, I don't think I have additional to add on. I think it's the motivation, the self-motivation is most important, right? And as you said, self-motivation and come up with the work ethics and I think the other thing is very important is resourceful. Resourceful meaning is you have initiative. So if you want to solve the problem, you should go out and find the solution, right? So I think that's part of the self-motivation.
That's true. Yeah.
Very good. Okay, we have Paul Chung here. He's another professor here, right? If no other additional comments or questions from the audience, I was asked by our organizer to probably just stop today's discussion here. Thank you so much, everyone, for coming to this seminar. And thank you all the people in the panelists, and especially our speaker, Jun, and also our organizers, Bingbing, Jen, and everyone for your time. And Bingbing and Jen, do you have any additional things to say before we finish?
Jen?
Yeah, thanks so much for Professor Chen's talk, and thanks so much for Professor He and Ruoxing and Professor Yang's host and Professor Yang's participation, and thanks everyone for attending our talk. And I think it's just like one more. It's just like a trailer for the next talk is on 3D printing by Professor Professor Yunlong Tang from Monash University. So see you in the next talk. Yeah. Thanks everyone.
Thank you. Thank you, Professor Yang. Thank you, Ximin. Thank you.
Thank you.
Thank you, everyone.
Thank you.
Thank you,
Thank you, everyone.
All right. Bye.
Here, bye.
Okay.
Thank you.
Thank you.
Bye.
Thank you. Bye. Have a nice weekend.
Yeah. Have a great weekend.
You too.
Bye-bye.